My Korean's very little, so 안녕하세요. And that's all of it. So hello everyone, and welcome to the talk about tips and tricks for optimizing Unity UI. This talk will entirely be focusing on Unity's built-in UI system and will contain a combination of presentation slides and in-editor demonstrations. The talk will cover common areas that developers have problems with when building UI systems and highlight how you can investigate to optimize it. I will also be showing some upcoming features, such as the UI profiler coming in Unity 2017.1, and how this can be used to optimize your Unity UI. My name is Andy Touch, and I'm a product content evangelist at Unity Technologies. And I have a job of 3 parts. The first part is to build feature demos and content using the new features that Unity is creating. The second part is to travel the world and instruct users how they can use Unity to build better games and non-games. And the third part is listening to feedback and looping this into our R&D teams to make Unity better for everyone. This is my very first time publicly speaking in Seoul, and I'm very happy to be here. And thanks for everyone coming this early in the morning at 11:20. So Unity UI was released in Unity 4.6 quite a few versions ago. And it was designed to be a built-in UI system for different kinds of user interfaces. It was designed to be flexible and generic, allowing for Unity users to design a UI system and then build it. The system is structured around a parent and child structure, where you have a canvas parent and a series of child elements, such as images and text, that build it up. It's with this generic design that some optimization problems take place. I typically split UI components into 3 areas. The first one being visual components of what is actually rendered, such as text and images. The second one is interactive components, and these are ones that take your rendered elements and turn them into buttons or sliders or toggles. And this is then influenced by the pointer. So on a touchscreen device, when you tap the screen, that's going to send a pointer event. Same with a mouse. And I think in HoloLens it's the same as well. And there's also layout components, which structure and place UI elements in an order or a sequence. And I'm outlining these because understanding how all of these systems talk to each other is incredibly important in knowing how to optimize your UI. You may think that text is your bottleneck in your project, causing bad performance, when it could instead be a layout element. And Unity has some tools that can outline what the process is that actually is causing problems. In an ideal world, there would be a process of building UI and then clicking an Optimize My UI button, and auto-magically, canvas rebuilding's fixed, everything is fixed for you. Kind of like the Make MMO button that we are still working on. Not yet, not really. Unfortunately, this button does not exist, and I don't see it existing for a little while. In optimization in general, you will need to research and debug and profile your UI, or anything in your game, to understand what needs to be fixed. It's very dangerous to assume what is the problem in your performance, and it's good to always profile. And I know that Ian Dundor, who is over there, and several other speakers have outlined this, and I think I'll outline it again for the 4th time to make it very important to always profile and not assume. So this talk will cover a range of areas for optimizing UI. The trouble is this topic is very, very big, and there's lots of different areas. I have about 50 minutes. In realistic terms, this would be about 10 hours, 12 hours. So I'm going to go through some key areas that allow you to make quick changes to your UI to optimize it. And there's a lot more information out there other than what I'll be talking about today. The main trouble is that optimizing UI is case-by-case dependent. For example, a low-end Android device is going to have very different problems or very different issues to, for example, VR or a console game, Nintendo Switch. They all have their own different issues. Another problem is there's a range of styles. A 2D RPG on a mobile is going to have very different problems with UI in performance to a 3D racing game on console. For example, a 2D RPG on mobile is going to use a lot of text and a lot of effects, whereas on a racing game, you may have a lot of dials or sliders that are changing, but they are more static. So not all advice will work in all use cases. And as I said before a couple of slides ago, you really need to profile and understand what is actually your bottleneck. And always test on your target device. I meet a lot of studios that build their entire games in the editor. The editor runs smoothly on their mega PC, and then they build to their low-end Android device, and it doesn't work at all, and they're very confused. So always build to your target device and understand the performance at that point. And with UI systems and any tool, there's a balance between flexibility and performance. And a lot of Unity's UI components fit into the flexibility section. You can add shadows to elements. You can turn anything into a button. You can animate anything. However, you've got to understand which elements of this are going to cause bad performance. And Unity UI allows you to walk a very fine line in between both of these goals. In some instances, you may need to create your own workflow or write scripts to replicate a simpler, less flexible, but more performant UI function. One key area to keep in mind when optimizing UI or building a UI is UI batching. And this process is similar to static batching and dynamic batching in Unity. However, there is different rules. So a canvas in Unity UI will try and batch its children based on similarities in variables and properties. Having all of these combined will then send a message to Unity's graphics pipeline to then render these objects. So if you have 1,000 elements on a canvas that all had very different properties, these would all be sent to be drawn individually. And you want to combine and make Unity's graphics pipeline renderer, Unity's renderer, to not have to do too many calculations. The trouble with UI is it's often a composition of many different elements, such as a background, and then a graphic, and then a tiled graphic, and then text, and then particles, and so on. And each of these tend to be split into separate batches. So you need to know how the rules to combine them, and then how you can identify what is not actually being batched. Here are some of the key UI batching rules. And it's good to keep in mind these UI batching rules, not only when you're optimizing, but also when you're designing Unity UI, or designing UI for your game. One of them is that elements are on the same canvas. And I've seen quite a few times where there's characters in a game, and each will have their own canvas floating above the character's head for a health bar or a name. Each of these canvases will batch its children. They won't batch each other. So you may have 400 canvases. That's already at least 400 batches if they have elements to draw. UI elements will also try to batch if they use the same material. In some instances, and I'll show you in a bit in the editor, you may have to use different materials for different objects. However, if you have lots of different materials, even if they point to the same shader, it will cause separate batches. Another rule would be that they share the same Sprite asset. Developers typically will create a Sprite sheet beforehand or import their assets and build an atlas afterwards. And having different references for your Sprite atlas asset will cause different batches. Unity has a Sprite Packer tool that lets you to combine a lot of textures into one place to build an atlas. However, it's a bit of a black box, and we're creating a new tool for Unity 2017.1 called the Sprite Atlas that will allow this process to be a bit more flexible and have a little bit more control. Another rule that people forget about is if rect transforms are not coplanar to each other, then they will not batch. For example, if this stage was a canvas and each of these screens was a UI image, they're both at the same Z depth from where you are sitting. However, if one screen was slightly closer or slightly further away, then this will cause them to be batched separately, even if they have the same rules already applied. I typically find UI designers sometimes creating their UI with different Z depths for their stack of UI elements, and don't realize that this could cause potential batching, separate batches. And another one is masking. Some people go quite overboard with Unity UI masking, and if elements are being clipped by a mask, such as a child, they are children objects of a mask, then this will cause them to be split from potential batches, and I'll show this in the editor. We have two built-in tools that will allow you to identify batches in your project, and this is the Frame Debugger and the UI Profiler. The Frame Debugger was released in Unity 5.0, and it allows you to have a step-by-step walkthrough of all the batches in your project. This isn't exclusive to Unity UI. It will also show you lighting and image effects and objects and sprites. And it's incredibly powerful to see how your scene is being, how your game view is being composited. The UI Profiler is a tool in 2017.1 that extends the profiler window and allows you to have more information about your UI system. Kind of like how the CPU profile will show you scripts and physics and their cost, the UI Profiler will show you layout and rendering. And I will now switch to Unity to show you how both of these tools work. So here we have a very simple UI. For example, an RPG. It could be more complex, but for the purposes of this talk, it's enough. And we have here a variety of different elements of children and images and text. We also have a scroll list here. And if I turn on this frame rate counter, you'll notice it maintains 60 frames a second, but as I scroll, it will drop down to 25 frames. I've had it drop down to 17 before, which is not particularly good. This MacBook is a late 2013 MacBook, and this performance is not recommended. However, it's not a good idea for me to assume that this and optimizations here will work on something like an iPhone 5. So you'll need to make changes, profile in the editor quickly, but then profile on device to see if those changes yield better performance. You also have some sliders, some buttons. And what you can see in this top right corner, hopefully this doesn't break, is we have a stats window which has a batches count. So there's currently 40 elements being drawn by our camera. If we're using dynamic or static batching, you'll notice that this saved by batching count will increase when we fit into certain batching rules for those processes. We also have a triangle count, and we also have a vertex count. So we have 40 draw calls, or 40 batches currently taking place. And with the Frame Debugger, we can enable the Frame Debugger, And we have a step-by-step run-through of all the batches of our game view. And we can even step through them and see our UI being composited as we work through. As you can see here, no UI will be drawn. We then draw this background image, this kind of background tiled image, this element, and you can see how each of our UI elements are being drawn in separate batches. All the icons are separate. Not very good. And then it will finish. And the frame debugger allows you to select a particular frame, such as this one, select a particular batch, such as this one, and view some information, such as the shader we're using, the blend mode, whether it's culling on and off. We have our shader properties being used, such as it's using this map texture. And we also have very advanced information, such as vertices and indices. So it will give you some information, but we may want more information of why batches are potentially breaking. And this is where the UI profiler comes into play. If I go to the profiler, by the way, I'm using Unity 2017.1 Beta 3. But everything I'm going to show you is compatible in the latest beta, which I think is Beta 5. I just haven't upgraded the project yet. So you can go away and download and use everything I'm going to show you today. And what we have here is we have the profiler. So we have the CPU usage row that's showing information about scripts and rendering. And we have two new blocks, UI and UI details. If I scroll down, you'll notice in UI, we have a green section here and a blue section. The green is the current layout time and the time it's taken to rebuild the layout, whereas the blue one is the render time. We can select a specific point of our UI's a specific frame that's already been processed, and we can see as well that it's taken 0.7 milliseconds to redraw the layout. And if I show you, by scrolling this element, we get a cliff, as I like to call it. And during the scroll, it's taken 7.9 milliseconds just to scroll these elements. And I think this scroll list has 1,000 child UI elements of it, so you can see it's quite costly. Another thing you can see here is we have a batches and vertices line. So as I scroll, you can notice that we don't have too much of a change, but you can see here that as elements are being revealed by the renderer and not, or being rendered by the renderer and not, then the batch count is increasing and decreasing. If I select a particular frame, the most interesting point here is this bottom section. And here we have a breakdown similar to the frame debugger of all the canvases of our current game view. I have two canvases, one for the frames per second counter, and one for the canvas start, which is just the start of the talk canvas. And you can see here that we have a list of all the batches that are currently taking place for our UI canvas. And it should be about 39, I think. Yes, 39. And as we scroll through, let me just resize this. We have information about each batch. And you can see in this preview that as opposed to the frame debugger, which adds each of the batches in order, we can isolate individual batches and view what is actually rendered on them. For example, if we take, let's take one of these tiny little icons. It's quite difficult to see on here. We can go through and understand what's actually part of this batch. So you can see here we have a vertex count. We also have a reason for why a batch breaks. So these UI batching rules that I showed earlier on also translate into this UI profiler. And we can see here we have several different reasons for a batch breaking. Now, this isn't a perfect column, I'll be honest. It tells you what could potentially cause the batch to break, but it gives you a good signpost to where you need to investigate. So it won't optimize your UI, that button doesn't exist, but it will at least give you a direction of how you can optimize it. For example, each of these sprites or each of these images are different textures. You'll notice that we have different materials being used to render different objects. And we also have this option here of different rect clipping. And this could be any combination of UI batching rules. One is coplanar, lack of coplanar, so two UI elements of different Z depths. One could be it's being masked, and I think the other one is, I can't remember. Yes, but there's a whole range of different batch reasons that go into different rect clipping. We also get some information about how many objects are on this current batch. So you can see here that we have 25 objects on this particular one. And we also have a list of the objects that are currently in this batch. And quite a useful thing is you can double-click this batch, and it will select the object in it. So if I double-click the 25 objects, you'll notice in the hierarchy it will select all the objects to do with that batch. So very useful for identifying exactly what is in what batch and where you can select it. Instead of it saying, there's 25 objects in this batch, and then you have to guess exactly what is being put in this batch and why it wouldn't be. As you can see here, that all of our elements are using different textures. And our artist, there's one more thing I need to talk about. This preview window here will show you what your UI element is going to look like. So if I go to this section here, we can see that we have a big dark background. Sometimes this may be tricky to see, so you can zoom in and out of it. You can also detach it separately, kind of like the Sprite editor or the Sprite packer. And you can also preview it in different modes. For example, if all your elements are, in this case, black, we can preview it on a white background, and vice versa. You may have white text in a game, and you want to see white text, but on a checkerboard it's difficult to see. We can also view the overdraw of this current batch, and also a composite overdraw of all the different batches, part of this, all the different elements that are part of this batch. So as you can see here from the UI profiler, we have lots of different tiny little objects, and you might be able to see in this preview, that are all separate. So all these tiny little icons. If I go to one of them and find the asset, you'll notice that our UI artist has actually created all the assets as separate images. And there's a couple of things we can do here. One is we could go back to our artist, have a conversation, and get them to combine all of these manually, or use a tool to automate it. The other one is we can use a new Unity tool, or a new Unity asset called the Sprite Atlas. If I go to the Create window, and go down to the Sprite Atlas, we can create a new Sprite Atlas asset. I'll rename this to Unite. Actually, Legend of the Prefab Atlas. And as part of this asset, we have some various options to do with this atlas. One is the objects for packing. So we can drag and drop or assign individual assets, or we can actually assign entire folders. My UI is composited of 3 folders: UI backgrounds, sprites, and Unity Chan avatars. And I can drag and drop each of these into the Sprite Atlas, like so. And when I click Pack Preview, it's then going to generate this atlas for me based on these objects for packing. And you can see here we have all the different icons and different elements to do with this particular folders assigned to the atlas. We have a couple of other options. One is packing, such as rotation and type packing. For example, if rotation and type packing are enabled, you may have two elements leaking into each other. I've set this up so it actually does that. So when we click play, you can notice, for example, here with these icons, we have each of the icons, because they're tightly packed, leaking into each other image, which doesn't look too good. We also have an upside-down backpack. So what we can do is we can disable these options, regenerate a new pack preview, and see how it looks. And what you may notice is that we have now an 8 meg atlas. And you have some other options you can do to control the size and settings to do with the atlas. For example, if I had more platform modules installed, you could specify per platform settings. In this case, I don't really have extra modules. So if I set it to be, let's say, low quality, use crunch compression, just as an example, repack it. Please work. OK, yeah. You can notice that the atlas will actually go down to 244 kilobytes. But obviously, this depends on the quality you want and how your atlas is authored. You can make multiple atlases and actually reference them via script and switch them between HD and SD versions. And as we go into Unity, you'll notice that our batch count goes from 39 or 40 down to 14. We still have the same performance issue here with the scroll list. So let's have a look at the UI profiler to see what is actually happening. We still have our batch count, but we can now identify that all of these elements are on this particular batch. However, as we go through and select other objects that are part of this atlas, you'll notice that they're on separate batches. For example, this element here, even though it's part of our atlas, it's not included in this first batch. So obviously, we don't have an Optimize UI button, but we can go to this particular batch and look at the reason. It's a different material instance. By double-clicking on it, I can realize that my artist has been a little foolish. It seems like a simple issue, but we can then notice that they've put a separate material on this element. So like I said before, if different UI elements share the same Sprite asset, they'll try to batch together. But if they use separate materials, then this will break the batch. So I can delete that. And then as I delete that, you'll notice that the batches will then drop down. So you can go through the UI profiler and change and modify and see how you can optimize. Another one is different rect clipping. So by selecting different rect clipping, you'll notice that it's actually selecting all of the white text, if I detach that are part of the scroll rect. Now, we can't really work around this because we want our big scrolling list to be masked. So we may just have to accept that these will be batched onto a separate batch than the rest of the text in our game. However, if we go through, we can identify also that we have a big header, which even though it's part of our atlas, such as here, is put on a separate batch. It says a different texture, but that's partly because previous batches may break and not necessarily reveal the right reasons. But by double-clicking this header, I can examine it and understand why it's breaking the batch. And one common thing that people tend to do is they tend to put holder child elements or holder parent elements on separate Z depths. And you can see this by switching into 3D mode for Unity UI. Like so. I've seen this so many times. And people don't realize it actually breaks batching. So if I set this to be 0, go back to our UI profiler and resume, you'll notice that something happened. We had a big spike as the canvas had to rebuild, and we also had a little drop in our batch count. A drop in our batch count. So let's continue and see what else there is. So we have here a mask, and a mask will list a different material instance. And this is because this UnityChan avatar, which looks quite terrible on the outside edge, is actually using a child mask, as you can see here. And what a lot of people do is they tend to use masks for very small sections or very small visuals in their game, but have very large images as the element being masked. And this may seem like a silly fix, but one thing to do is only really mask things that you really need to have cut out by Unity. This may be unavoidable in some instances, such as a scroll list. However, for this avatar that doesn't change or doesn't really move, we can pre-cut this out and avoid the mask kicking off extra batches. So if I disable this masked element and have this pre-sliced one done manually and go back to the profiler, you'll notice that our batch count will actually drop to 9 batches. That's actually kind of tricky to see, so you can see it here. And as we've gone through and changed various elements of our UI system, you can notice that the UI profiler will allow you to identify not exactly what to change, but at least give you a good indication of where you need to look at. Let's switch back to slides. So showed off the Sprite Atlas. Sprite Atlas is a lot more to it than what I showed. There is an API where you can actually switch atlases at runtime, which is interesting. Unfortunately, I don't have time to show that right now. Another area that you could optimize is shaders. However, with devices getting faster and faster, it's not so much a big issue as before, but it's still a good thing to take into consideration. So all visual elements will use this UI/default shader. This is both for text and images. And this shader supports masking, clipping, vertex coloring, and various other operations. Not many people know this, but you can actually download all of Unity's built-in shaders as a package and modify them, change them, learn from them, and completely hack them apart. And all the shader source code can be customized. So one thing you can do is you could identify what needs to be masked and what doesn't need to be masked, and put all the non-masked elements using a custom version of this shader. For example, I have cheated and already made this. If we look at our UI, the elements we only want to be masked is this scroll list here. These elements up here are not being masked, so we don't want the operation of the masking for the UI shader. So I've taken the UI shader, removed masking, and applied it to all the elements. And you can see here, as I select an element, such as UnityChan here, we have a custom material, and they're all using the same custom material, which means they're batching together. And this custom material is using a faster version of this shader that doesn't include masking. And you'll notice that because all the elements, the text and the images, are using the same material, we still can have 6 batches because we're keeping in line with our UI batching rules. One issue with this is you'll notice that as I scroll the list, the elements are no longer being clipped because we've removed that functionality and are instead disappearing completely. This could be an issue if you want or designed your UI to clip as you reach a particular line or a particular point of your mask. However, going back to our UI batching rules, all elements of a mask will be batched separately, so we can actually afford to go to the UI elements part of the mask and put them on their own separate material, and not lose or gain any extra batches. For example, if I go to this scroll element here, and go to the children, they're all using this UI fast material, and by removing that for each of the elements, this will allow them to be fall back to the built-in UI shader, or the built-in UI shader material, which has support for masking. We can then scroll, and you'll notice that I made a rookie mistake and didn't apply the prefab. We've all done it. That as we scroll, you'll notice that it's no longer being hidden instantaneously. It's actually being clipped across the element. But we still maintain the same batches, because we're still within the UI batching rules. Because these elements are being masked, they're batched separately from other elements, so we can afford for them to use a separate material. Another area that you could look into is TextMesh Pro. So this is a new asset. It's an asset that's been around for a while, and it allows text customization and text rendering that's different to Unity's built-in UI. It's very popular at Unity Asset Store package. I'm sure many of you have heard of it. And we've actually acquired it recently to then be given for free to Unity developers and eventually integrate in some form into a future version of Unity. And it's free to download today. If I go back to this UI canvas, there's a couple other scene views you can use to identify performance problems. One is the wireframe mode. And what you'll notice is for our text, for the header here, Legend of the Prefab, we have each character being drawn multiple times. This isn't actually drawing the character multiple times. It doesn't increase batches. It's just adding extra points on the mesh. So for this character of L, you can see that there's almost there's about 4 or 5 times it's being drawn on top of itself. And the main culprit of this is shadow and outline components. And I've seen so many times people put these shadow and outline components on many different elements. If I go to this text header, you'll notice that we have outline and shadow. And this goes back to what I was talking about before, in that a lot of Unity UI components are built generically and very useful for quick flexibility, but not necessarily performance. And as I disable and shadow and outline, you can see that these are actually the culprits. And what they do is they take the object and add more vertices, more triangles, and kind of draw it again, but without adding extra batches. If we go to overdraw, we have a heat map of all the elements that are being drawn, and kind of you can see the fill rate. And here you can see that we have a very bright orange heat map for our text as it's being drawn multiple times. So this could be bad, because a lot of devices can only afford a certain amount of elements being drawn on the screen, and you kind of want to take your composition of UI and compress it and combine it, or limit the number of times that a pixel on the screen is going to draw multiple transparent objects. In general, you shouldn't really use shadow and outline for any UI element. One solution, and you'll have to test this out for yourself, as it's a big topic in itself, is TextMesh Pro. With TextMesh Pro imported, you can go to Game Object, UI, and TextMesh Pro, and you can place TextMesh Pro text elements onto a canvas, so it works with Unity's built-in canvas. And as I add a TextMesh Pro text element, you notice it's very similar to UI text, in that you have a box with a rect transform, and you have some text that you can then change. So let's say, I'm not going to write anything in Korean. Let's do hello, Seoul. However, TextMesh Pro renders text in a slightly different way. It renders using sign distance field, which basically means that it works out the distance that the text element should be, or the text pixel should be, from the edge. So if we zoom into this Legend of the Prefab text, you'll notice that as it's an image, eventually as you scale it up or scale it down, it's going to lose a lot of its quality. If we go to this Text Mesh Pro element and keep zooming, you really have to go inception deep to see some form of artifact. And because it uses this process, it means we can add a lot of effects to this without extra cost of extra triangles, vertices, or overdraw, or fill rate. For example, we could modify the dilation of the text. And what you'll notice in wireframe mode is that as I change the dilation of the text, there's no actual, well, there's a change in size, but it's not really changing or drawing the element multiple times. We can also add a very subtle outline, modify the dilation, add a drop shadow, add a bevel, lighting, so let's change the lighting to green, why not? You can add a bump map. You have lots of different options that you can apply to Text Mesh Pro text. And because it's using signed distance field rendering, we can go to the wireframe and notice that it's not drawing the element multiple times. And it's also maintaining good quality as we zoom in. So you can change your text using Text Mesh Pro and have very different results. So if I delete this element here, if I enable this Text Mesh Pro version of this panel and put it side by side. So the one on the left is using Unity UI text, and the one on the right is using Text Mesh Pro. If I go into wireframe mode, you can notice that the header here with shadow and outline looks like this and has a kind of a fuzzy edge. And there's a pretty big heat map in terms of overdraw. If I go to the Text Mesh Pro version, it looks a lot crisper. The wireframe isn't drawing the characters or adding extra vertices to it. And the overdraw is less, because it's not having to draw the same element over and over again. So before, if we do a comparison in terms of triangles and vertices, we have 4.1K triangles and 11.1K vertices and 5 batches on this canvas using Unity UI. So 4.1 and 11.1. If I enable the Text Mesh Pro version, five batches, 1.8, and 3.6. And this is quite a simple UI, but you think of a lot of games that have a lot of text and a lot of effects and shadows. This could be a big saving. I'm quickly running out of time, so I'm going to go through these next areas quite quickly. So another area to look into is the rebuild process. And this is where an element on a UI canvas changes and needs to be redrawn or rebuilt. I'm going to talk about this at kind of a high level, but there's lots of information written by Ian Dundor, who's sitting over there, going way more in depth into this process than I have time to. So if your UI element layout changes, so this is an element being affected by a layout component, and it changes in some way, then this will set the element to be dirty. And if a graphic changes, such as changing color or material or an image, then this will set it to be dirty. This will then send these to the rebuild process, which recalculates the dirty components and objects. And if you've looked at the profiler, you've often seen this under canvas.send will render canvases. And this is the process for the rebuilding of the canvas. A lot of people don't know this, but the Unity UI source code, about 90% of it is actually available and written in C#. So if you go to the Unity Bitbucket page, you can actually download the Unity UI source code and dig into the components and learn how they're structured. It doesn't include all components or all processes. It doesn't include the rect transform component, because it derives from the transform component, which is native into Unity's source code. It doesn't include the canvas component as well, because that's tied into Unity's batching process, which is internal as well. And it doesn't include canvas group, because that uses elements from a canvas as well. But the majority of everything else is available for you to download. If I go to the page, you can notice here that we have lots of information about the UI source code. And it's split into three sections, several sections. One is the actual editor UI, so how it's presented in the editor. One is the actual Unity engine.ui. This is the actual functionality of the UI. And the other one's Unity engine.ui-editor. However, the one I tend to spend most of the time studying is Unity engine.ui. And the Wi-Fi won't work, which is fine because I already downloaded it. So under Unity engine.ui, you'll notice that we have several folders. If we go into the UI folder, into the core folder, you can recognize some very familiar components or very familiar classes that you can look at, such as if you're curious how the drop-down component works in Unity's UI, you can study this, or an input field, or a mask, or an image. And you can go in and analyze how these UI elements work, and then instead of making assumptions on where to optimize, you can then study them and actually see where you can optimize your UI in different ways and what's happening. I'm now going to very quickly, because I have a few minutes left, go through a couple of key areas. One is graphic.cs, which is a graphics class. And any visual element is using this, such as text and images. And there's one method here, which is onRecTransform dimensions changed. It's quite self-explanatory when this takes place, but you'll notice that we have a setVerticesDirty method call, setVerticesDirty, and setLayoutDirty as well. So when a rectransform changes on a graphical element, or the dimensions change, it will trigger these methods. Another interesting part are these two, and Ian Dundor spoke about them very briefly in his talk. And it's onBeforeTransformParentChanged and onTransformParentChanged. So even though this graphic class is used by an image, it also has calls to other elements, such as the parent. So if you have a parent rectransform with an image as a child, and you move, this could trigger off multiple calls to other objects, not necessarily just the image. And you can see here we have layout rebuilder, marking the layout for a rebuild. That's part of that rebuild process. And layout rebuilder is a class you can dig into and then look at as well. We have this method here, setAllDirty. So what does setAllDirty do? It runs these three methods: setLayoutDirty, setVerticesDirty, and setMaterialDirty. If I go back to the previous slide, you can see that when a parent of an element using the graphic class changes, it sets the child to be dirty. So moving a lot of elements via the parent could potentially cause various dirtying of elements and therefore requiring rebuilds. SetLayoutDirty will then go to the layout rebuilder, mark the layout for a rebuild. SetVerticesDirty won't mark the layout for a rebuild, but instead will register this graphic for a rebuild. Remember I said layout elements being rebuilt and graphic elements being rebuilt? And the same with material. And then you can keep going. It's kind of like Alice in Wonderland rabbit hole. You can keep going and seeing and digging deeper and deeper into what is actually happening. I have 44 seconds and a few more slides. So layout components can be vertical, horizontal, grid, and layout elements. These are actually incredibly useful for structuring Unity UI and placing them in an order. However, lots of related rectransform changes could cause the layout to be dirty, which is why when I scroll, the scroll rect, that's changing the parent's position of 1,000 child elements, and all of those are kicking off lots of processes all the way up. Many elements being put into the rebuild process causes lots of processing time to rebuild the canvas or rebuild the layout. Let's look at layout group class. This is used by vertical layout, horizontal layout. It's also being used by the scroll rect component as well, which I didn't realize until Ian pointed that out to me. Thank you. And you can see here that when we enable a layout group, it's going to set it to be dirty, which is why when you turn on and off a layout group, it's going to have a spike because it has to set dirty all the elements and rebuild them. When we disable it, it marks it for rebuild. And this one, on did apply animation properties, will set it to be dirty as well. So if you're using the animator, this could potentially cause lots of dirtying of elements and lots of rebuilds of your UI. Another method, on rect transform dimensions change, very similar to the graphic class, set dirty. On transform children changed. So if you have a layout component and it has a child has changed in some way, it also sets it to be dirty. You can see a recurring theme here, and lots of things can set your canvas to be dirty. So what does set dirty do? It marks it for a layout rebuild. Not a graphical rebuild, but a layout rebuild. And there's a couple of suggestions to talk about here. I'm basically out of time. One is to enable layout when it needs to be rebuilt. Another one is to use a smaller number of child elements on your canvas. Another one is to create your own layout manager script. Rather than relying on Unity's layout to place things above or below each other, you can very easily, if you know how to program, write your own version of this. And the other one is an object called scroll list. For example, in my UI, I have 300 inventory elements, but I only see about 8 at any one point. So what you could do is you could draw 8, and as you scroll, kind of like a conveyor belt, reuse them one by one and position them. Although we're positioning them and triggering off a rebuild, you're repositioning 1 or 5 every time, not 100, including their child elements, which would be 1,000 or something like that, 300 to 1,000. And there's this magical button, which lots of people like ticking, and I don't like it when people tick it. And that's pixel perfect. And this is quite useful on the canvas, for when a rect transform moves, it snaps it to pixel edges. The pro is you get pixel perfect visuals, and things look very crisp. The downside is as you scroll, all the elements of that canvas are constantly snapping to the right pixels. The animator can also kick off lots of canvas rebuilds. And you see here, set all dirty on the graphic class. So if you animate any element using the animator, this could cause things to be dirty. And I know I'm out of time, but I need to point this out. One solution would be to sub-canvas things. So rather than having one big canvas with lots of different child elements on it, you can actually add a canvas component to children. This will create a sub-canvas, and it can be used to isolate canvas rebuilds. Lots of people taking photos, so I'll switch to Unity quickly to show this. I have here the same UI setup. Still 5 or 6 batches. And as I scroll, you'll notice that the frame rate will drop from 60 down to 26 or so. If we look at our canvas, we'll notice it's using pixel perfect. So as we scroll, all those child elements are snapping. They're triggering off parent and triggering off all sorts of rebuilds of our canvas. One solution is to take our dynamic elements that move or change or animate and put them on their own canvas and isolate the rebuild. So if I go to this inventory element here, add a canvas. So I've now got a sub-canvas. We can actually not inherit pixel perfect. Because we're interacting with the element on the canvas, we have to add a graphic raycaster so we can click it and move it and select it. Because our static UI is using pixel perfect and not moving, we can afford to use pixel perfect, although generally you should really try and design your UI not using it. However, with this sub-canvas, as I scroll the elements, pixel perfect's not going to snap them to nearby pixels. So as I scroll this, the performance will be better. But this is on my MacBook. Try doing this on a mobile device and seeing what problems you may have there. The other thing to take note of is my batch count has actually increased. And the UI profiler, as you'll notice here, will also show you the sub-canvases and their batch amounts. So we have the sub-canvas with batches 0 to 4. We then have another child, which has its own batches, batching its text in images. So you have a trade-off between batches, layout rebuilding, and having to balance between what is the expensive process, or where your bottleneck is going to be. I am massively over time, so they're probably never going to invite me back to talk again. But the Unity UI source code, I recommend to download it, study it, analyze it, and look through it. You can also modify it, but I tend to find people actually use it more for learning purposes than modification purposes. If you just Google Unity UI source code, it will probably be the first link. The other one is Unity UI Best Practices Guide. So we have some best practices for physics, asset bundles, and UI. A lot of things I spoke about are in this guide, but they go more in depth and a lot more information and a lot more examples. So as I said, I'm constrained to a 15-minute, 1-hour talk, but optimizing UI can go a lot deeper and a lot further than what I showed. But hopefully this has been a good jumping in point to learn how to optimize UI. I'm in negative time right now, so rather than doing a Q&A, I'll be at the Unity Connect booth around there. If you want to come say hi, talk about UI, I'm also into shaders and timeline and all sorts of interesting various things. Come up and say hi. Thank you for coming and attending a UI talk, and kamsahamnida.